At this moment, thousands of satellites are operating above Earth. Now imagine that. Without warning, all of them stop working. GPS disappears. Weather monitoring weakens. Remote communications begin going silent. Aviation, shipping, agriculture, telecommunications, and emergency services all feel the effects. The strange part is that the world would initially look completely normal. No explosion, no darkened skyline. Your coffee machine remains emotionally unaffected. But underneath the surface, modern systems begin losing position, communication, and precise time, and losing time may be far more disruptive than losing maps. Before disabling everything, however, let's begin with one malfunctioning satellite, because satellites do fail, and engineers plan for exactly that. The real question is how much failure the system can absorb. A satellite is essentially an autonomous computer operating in an extremely hostile environment. It must manage power, temperature, orientation, and communication, with no technician available. When something unusual happens, onboard software attempts to identify the problem. Many spacecraft respond by entering safe mode. Non-essential equipment is switched off to conserve power and reduce risks. The spacecraft may orient its solar panels toward the sun. It also tries to remain stable and maintain communication with mission control. In practical terms, the satellite stops working and concentrates on staying alive. Engineers then examine telemetry to determine what caused the anomaly. They review power levels, temperatures, software events, and the spacecraft's orientation. A failed component may be isolated and replaced by redundant hardware. Sometimes the solution is a software update or a carefully controlled restart. Apparently, turning it off and on again remains valid several hundred kilometers above Earth. Meanwhile, other satellites or ground systems may temporarily cover the missing service. Most people may notice a short outage, or nothing at all. Redundancy makes one failure manageable. Multiple failures are more interesting. Satellites operate through radiation, vacuum, rapid temperature changes, and years of mechanical stress. A high-energy particle can pass through electronics and alter stored information. A single corrupted bit can confuse software or trigger protective systems. The computer may briefly become uncertain about where it is or where Earth is. Solar activity can also interfere with electronics, radio signals, and navigation accuracy. Strong solar activity can heat the upper atmosphere and increase drag on low satellites. That changes their orbits and forces operators to make additional corrections. Mechanical components can fail as well, including devices that control spacecraft orientation. If a satellite cannot point correctly, its antennas and instruments become far less useful. Incorrect orientation may also prevent its solar panels from generating enough power. Batteries degrade, fuel runs out, and electronic components gradually age. Software errors are another possibility, despite extensive testing before launch. Once the satellite is in orbit, returning it to the manufacturer becomes inconvenient, and even a functioning satellite can be damaged by orbital debris. Usually the problem is contained, but what happens when an entire service fails? Consider satellite navigation systems such as GPS, Galileo, GLONASS, and Beidou. A receiver compares precisely timed signals from multiple satellites. From tiny differences in arrival time, it calculates its position. If enough satellites fail, positioning becomes less accurate or disappears entirely. Your phone still has a map, it simply becomes less certain where you are on it. Aircraft do not immediately fall from the sky. They use procedures and alternative systems. Ships also have radar, charts, inertial systems, and conventional navigation methods. Operations would continue, but with less efficiency and larger safety margins. Precision agriculture, surveying, construction, and automated machinery would also be affected. Logistics would become slower, especially where location data is heavily automated. But navigation satellites provide something even more important: precise time. Telecommunications networks use synchronized timing to coordinate signals and transfer data. Power infrastructure and financial systems also depend on accurate timestamps. Backup clocks can maintain operations, but their accuracy gradually drifts. At infrastructure scale, tiny timing errors can become expensive problems. Communications satellites connect aircraft, ships, broadcasters, remote communities, and emergency operations. For isolated regions, satellite links may be the primary connection rather than a backup. Most urban internet traffic would not vanish because terrestrial cables would still exist. The underwater cables from the previous video would continue carrying most international traffic. After years of being ignored, the cable network would briefly enjoy excellent publicity, but satellite-dependent users would experience immediate communication gaps. Weather satellites present a different problem. They provide broad, repeated observations of clouds, storms, oceans, temperature, and atmospheric moisture. Ground instruments would remain, but they cannot provide the same global coverage. Forecasting would become less accurate, particularly over oceans and remote regions. Major storms would still be detected, but their development could be harder to monitor. Wildfire, flood, sea ice, crop, and environmental monitoring would also lose major data sources. Emergency teams would have less current information during exactly the situations that require it. Now combine every one of these failures at the same time. In the extreme scenario, every operational satellite suddenly stops functioning. Navigation, timing, weather observation, remote communication, and Earth monitoring are disrupted together. Electricity does not immediately disappear, and terrestrial networks continue carrying data. Ground systems, fiber networks, radar, radio, and local timing sources still exist. Well-prepared organizations switch to backup procedures and alternative technologies. Remote regions, maritime operations, aviation, and satellite-dependent industries face the largest immediate impact. As time passes, reduced information and degrading backups make operations increasingly difficult. The result is not instant collapse. It is slower, less precise, and more expensive coordination. Civilization survives, although considerably more of it may involve telephone calls and paperwork. Rebuilding would require replacement spacecraft, launch vehicles, ground testing, and international coordination. Restoring complete global coverage could take months or years depending on the system, and the failed satellites would not simply disappear. They would remain in orbit as uncontrolled objects that cannot avoid collisions. A functioning satellite can maneuver when a collision is predicted. A dead one cannot. A collision can create many fragments, each moving at enormous relative speed. Those fragments increase the risk of further collisions. In the worst case, repeated collisions could create a self-sustaining debris cascade. This theoretical process is commonly called the Kessler syndrome. It would not turn the entire sky into an explosion within 5 minutes. But over time, some useful orbits could become increasingly hazardous to operate in. Satellites are not civilization itself. They are the layer that helps civilization coordinate. So which would cause more damage, losing the satellites or cutting the underwater cables? Like, comment, and subscribe for more.